All right, guys, so with this lecture short, well, it's not really short, but with this lecture, I'm going to cover section 5.2 out of your book, which is calorimetry. And this is probably one of my favorite topics to cover in chemistry because it really just simply boils down to thinking about who's losing heat, like who's getting colder and who's losing heat and who's absorbing that heat. So that's really all these questions boil down to. All right, so let's get started. All right, so there's two learning objectives for this section. The first one is to explain the technique of calorimetry. So we're going to define what calorimetry is and then give you a couple different types of calorimeters so you can explain the technique of calorimetry, how it's used, what does it solve for, and what types of equipment can you use for it. The second learning objective is to calculate and interpret heat and related properties, calculate and interpret heat and related properties using typical calorimetry data. So we're going to get a lot of temperatures in our data, and usually you have some masses of things too. So you're going to have to be able to generate your own formulas, which shouldn't be that hard when we think about the conceptually what is going on in calorimetry. But you'll generate your own formulas and solve for variables. All right, so let's start off with defining what calorimetry is. So calorimetry is a technique used to measure the amount of heat involved in a chemical or physical process. So chemical processes are like chemical equations or chemical reactions, right? You take two things, you mix them together, you get two new things. So reactants turning into products. Physical processes are the ones where we're just talking about phase changes. So ice melting, right? So solid to liquid phase change. Liquid evaporating, so liquid water turning into gaseous water vapors, right? So just physical changes. In calorimetry, we're going to be measuring the temperature of a lot of these things and figure out how much heat is involved with that change or that process. So when we think about calorimetry, like I said, we always are talking about something's going to be losing heat and something's gaining heat. All right, so we define two things. We have a system and we have the surrounding, okay? So the system is the substance or substances undergoing the chemical or physical change. All right. The surroundings are referred to as all other matter, including the components of the measuring apparatus, which is just a fancy way of saying including the thermometer that you've got in your solution, that serve to either provide heat to the system or absorb heat from the system. So don't get bogged down by that definition of the surrounding. The surrounding is just everything else that the system is coming into contact with that's able to, provide energy to, either release energy into the surrounding or it's going to pull energy from the surrounding. Okay, so that's the system and the surrounding. And when we work our examples, we'll define what's a system and what's a surrounding every time. All right, so the way that you can perform calorimetry experiments is through a calorimeter, which is a device used to measure the amount of heat involved in a chemical or physical process. One of the most basic, easiest types of calorimeter, which you'll actually be working with in lab on Wednesday, is a coffee cup calorimeter. You take two styrofoam coffee cups and stack one on top of the other, you've made yourself an awesome calorimeter, right? It's insulated a little bit, so it holds most of the heat that's generated or absorbed doesn't come from the coffee cup itself. It's just coming from the reaction or the physical change that's occurring inside, right? So you've got two coffee cups with a lid. You've got something in there to stir. I think honestly in lab, you guys are just gonna kind of swirl your cups to stir. And then you've got a thermometer to actually measure the change in heat, right? Because everything in calorimetry is talking about heat transfer. Something's losing heat, something's gaining heat. All right, so that's the most basic type of calorimeter, and it's inexpensive, reliable, it works. The next type is a little more expensive, but it's still a solution calorimeter. It's just a bona fide coffee cup calorimeter, essentially. So instead of two styrofoam cups, you've got metal cans, you've got a canister with an insulating support ring, so that you can put your reaction or your phase change in this smaller internal pail. You've got your stirring rod, you still have a thermometer and a lid. So see, it's just a metal version of a coffee cup calorimeter in so many ways. But the most expensive is what we call a bomb calorimeter. So the bomb calorimeter actually has this little internal bomb that goes off with water surrounding it, and you measure the change in temperature of the water. Okay, so inside this bomb right here, you can see you've got your little sample tethered through a couple wires, and then this chamber is pressurized. That internal chamber is pressurized with oxygen gas, so there's a bunch of oxygen gas in here around your sample, and then you add a little spark through your electrodes, and then that combustion reaction occurs in the bomb, right? And combustion reaction releases a lot of heat into the surrounding, and so you see you measure the increase of temperature of the water over time. So probably up here on our screen, it'll say, 23.8. You're going to monitor temperature over time. So those are the 3 types of calorimeters. You'll only use the coffee cup one in lab. All right, so when we have a reaction or a phase change going on in one of those types of calorimeters, you can explain or describe the reaction in one of 2 ways. You could describe it as an exothermic process or an endothermic process. And remember from our first lecture that Q is the sign, is the variable for heat, right? So an exothermic process releases heat into the surrounding. So the system is going to be pumping off heat. It's generating heat. And then the surrounding is going to be absorbing that heat, okay? So if you, for example, feel something that's hot to the touch, even if it's like at home, you grab the pan off the stove and it burns your hand because it's hot. The pan was the system and your hand was the surrounding. So your hand absorbed the heat from the pan, right? That was an exothermic process. It released heat. The pan released heat into the surrounding. And we say that's a negative Q. So the sign here doesn't indicate like a negative value per se. The negative sign here means release. Okay. Dang it, sorry. The other type of process reaction would be an endothermic reaction. So that's positive Q, all right? And that's when the system absorbs heat from the surrounding. So if you feel something, grab something, and it's cold to the touch, that is absorbing heat from the surrounding. So when you touch an ice cube, the ice cube is absorbing heat from your hand. That's why it feels cold. And this positive sign right here, again, doesn't mean that's a big positive magnitude value. It just means the positive is talking about it's absorbing the heat. Right? So if you look at the 2 examples up here in our pictures, we can see that an exothermic reaction would cause the surrounding solution of the chemical reaction to increase, right? Because remember, the exothermic reaction is releasing heat, so the solution or the surroundings are absorbing that heat, so they're going to increase in temperature. Now, if the process was endothermic, remember endothermic reactions have to absorb heat, and that heat that they're going to absorb comes from the surroundings, so you should actually see the temperature drop or decrease. Okay. All right, so then here's where the math starts to come into play. So the heat of the system is equal to the heat of the surroundings with just opposite signs. Okay, so they're equal in magnitude. That would be like saying 50 joules is going to be equal to negative 50 joules. Okay, mathematically that sentence makes no sense because positive doesn't equal negative, but this is not math class, it's chemistry class. And heat, the sign in front tells the scientists whether or not that reaction is releasing the heat or absorbing the heat. So remember, the negative is an exothermic process, and that's releasing heat. And the positive is an endothermic process, and that's absorbing heat. Okay, so what's nice, what I like about calorimetry is that the magnitude, the value between the system and the surrounding will always be the same. It can't change because thermal energy is neither created nor destroyed, it's just transferred. Okay, so you can't lose it. The negative sign or the positive sign, usually you'll get when you calculate your delta T, your change in temperature. But again, if you don't have to calculate that, you can just always think that the negative, you have to think about what the problem's saying and then figure out who's releasing energy and who's absorbing that energy. Okay. All right, so let's work a problem. All right, so here's an example, identifying a metal by measuring specific heat. So a 59.7 gram piece of metal that's been submerged in boiling water was quickly transferred into 60 milliliters of water initially at 22 degrees Celsius. The final temperature is 28.5 use this data to determine the specific heat of the metal. So here we are with that learning objective number 2. So interpreting these numbers, this data, and figuring out what they want. When they want specific heat of the metal, so they want CS of the metal. All right. So you have to know a couple things here. And likely, I will give you the specific heat capacity of water, but you use it so frequently, it's 4.184 joules gram degree Celsius. So that's specific heat capacity of water. And then you'll have to remember the formula for specific heat capacity. Specific heat capacity of anything is equal to the amount of heat divided by grams change the delta T. So change in degrees Celsius, like per degree Celsius. So, okay, so those are some numbers and formulas we'll need. And then remember, let's define what's our system and what's our surrounding. So probably we got to think about this as going in a cup, right? I've got 60 milliliters of water. I've got that metal piece that was sitting at 100 in boiling water. So it was at 100 degrees Celsius originally, right? You drop the metal in water, the metal's going to give off heat, right? And heat up the water. So the system is the metal and the surroundings is the water. Okay, so here, there's some more things that are the surroundings technically. So we had a thermometer sitting in here, right? The surroundings is also the thermometer, because the thermometer would have to absorb some of that heat. That's how you actually see the change in the thermometer, right? The temperature going up. And the cup or the beaker or flask or whatever it's sitting in, the vessel, is also the surrounding. So that's going to absorb some heat as well. But we are going to assume, for the sake of this question, that the thermometer, the amount of heat absorbed by the thermometer is negligible, and the amount of heat absorbed by the vessel is negligible. The reason we assume that is because they didn't tell you what the heat capacity of the calorimeter was. So they would give you like C-cal if they wanted you to include the amount of heat that the vessel would absorb as well. So good news is we don't have to worry about that. So when we think about that last thing, so the system is the metal, right? It was at boiling, and then it's going to be at a final temperature of 28.5. That means that it is releasing energy. So that's going to be our negative Q. That means that the water has to be our positive Q. Okay. So we can say negative Q metal equals positive Q water. And this is just because we say that the negative Q of the system equals the opposite sign Q of the surrounding. All right, but now we kind of rearrange our specific heat capacity for Q. So you can say Q is equal to CS times mass times change in temperature. And you plug that in for both the metal and the water. Okay. So we would say that our negative heat capacity, which is what we're solving for, the specific heat capacity of the metal, times by the mass of the metal, 59.7 grams, times by the change in temperature of the metal, delta T metal, we got to calculate that real quick. Let's see, final minus initial. The final temperature is 28.5, the initial temperature was 100. So what does that equal on a calculator? I'm going to pull up a calculator real quick, if I can get it on my phone. So what is 28.5 less 100? That's going to be 71.5 degrees Celsius. And what's the T of the water? Let's see, the final temperature of the water was 28.5 and the initial temperature was 22.0. So what's 28.5 less 22? 6.5 degrees. So see, the metal cooled down 71 degrees and the water warmed up 6 degrees. Sorry, that should be a negative sign right there for the metal, right? Negative 71. And that negative sign is this same negative sign right here that I put out in front, because that negative sign is letting me know that Q is releasing the water. So I'm just going to write that 71.5 here. I'm not going to put a negative because that negative and negative would cancel out. Okay. All right. I'm actually going to do a little bit of erasing to give myself some room. So we calculated the delta T's there. Let's just erase and go back to our question. All right, so that equals the positive Q of water. So that's 4.184 joules gram Celsius times the mass of the water. Okay, we have 60 milliliters of water. Wait a minute, density of water is 1 gram per milliliter. So if I have 60 milliliters, that means I have 60 grams times the change in temperature of the water, which was 6.5. Okay, so if we divide by negative 59.7 times 71.5, we divide by negative 59.7 times 71.5. All that cancels. It's going to leave me with X. So I could say X, which is the specific heat capacity of the metal, is equal to this math. So 4.184, calculator, 4.184 times by 60 times by 6.5 divided by 59.7 divided by 71.5. And that is 0.382 joules, yeah, joules gram degree Celsius. Bling. So then, if you can use the result to identify the metal, there's a table in the book, and I think it's on my next slide. Did I put it in here? No, I didn't. All right, well, there's a table in the book you can compare your value to and see what metal it is based off the specific heat capacity. All right, so let's do an experiment that has that uses the coffee cup calorimeter. So the coffee cup calorimeter, remember, inexpensive, reliable, you're gonna do it in lab. The one thing to note about coffee cup calorimetry though is it's under constant pressure, right? So this is all sitting in the atmosphere. Nothing's like sealed so that the pressure can't change. So everything's under constant pressure, which would be atmospheric pressure. All right, that's just something to note. That will come into play actually next section, but I just want to point that out, constant pressure. Okay, so here's our example. Heat produced by an exothermic reaction. Exothermic, you already know, it's going to release heat because that's what exothermic means. All right, when 50 milliliters of 1 molar hydrochloric acid and 50 milliliters of 1 molar sodium hydroxide, both had been sitting originally at 22 degrees Celsius, are added to a coffee cup calorimeter, the temperature of the mixture reaches a maximum of 8.9 degrees Celsius. What is the approximate amount of heat produced by this reaction? Ooh. All right, so let's define our system and our surrounding. So it sounds like to me you're mixing 50 milliliters of acid with 50 milliliters of base. Okay. And that is an exothermic process, so that heat is being generated and released, and it's getting absorbed by something. So what's actually generating the heat, though? Is it the cup? Is it the acid? Is it the base? Or is it the water? So this is a little more tricky. Well, it's not really tricky, but you got to think about what does this mean to be an aqueous solution, an aqueous something. So that means that you took a solid and you dissolved it in water, and you've got aqueous. So the bulk of the 50 milliliters of base or acid is really roughly 50 milliliters of water with just a tiny, teensy amount of sodium hydroxide molecules in the water. Okay, so our system is the chemical reaction. That's the molecules of HCl reacting with the molecules of sodium hydroxide. The surroundings is going to be the water that you dissolve, that you created these different solutions with. So the water and the cup, you know, and the thermometer, right? So the cup that it's sitting in, the thermometer, but again, negligible amount from the cup and negligible amount from the thermometer, as we have to assume that. Okay. So it sounds like to me that if we can figure out the amount of heat produced by this reaction, right, negative Q of our reaction, because that's our system, is equal to the Q of the surroundings. And the Q of the surroundings, oh, look, the surroundings are just water. So if we can figure out, remember Q, if we can figure out, plug in from our last one, the specific heat capacity of water times by the mass of water times by the change in temperature of the water, we should be able to solve for Q of the reaction. And the Q is going to be negative, right, because it's exothermic, it's being released. So really it's a plug and chug. So what's the specific heat capacity of water? 4.184 joules gram degrees Celsius. The mass of water, oh, how much water do we have? We mix 50 milliliters of this aqueous amount of hydrochloric acid with 50 milliliters of this aqueous amount of sodium hydroxide. Like I just said, that those solutions are, the majority is only water. It has a few molecules of HCl, but it's mostly water. So in total, we have 100 milliliters of water. We have to assume that. And so if we have 100 milliliters of water and the density of water is 1 gram per milliliter, that means that we have 100 grams of water. What was our change in temperature of the water? Well, both of these things were at 22 and the final temperature was 28.9. So we're gonna have to calculate the delta T there. So 28.9 less 22, and I get 6.9 degrees Celsius. All right, so let's just plug and chug. So if we take our change in temperature, multiply it by the mass of water, which was 100 grams, multiplied by the specific heat of water, which is 4.184, I get 2,886.7. How many sig figs do I need though? I just need 3. So 2,890 joules, negative Q reaction. So if you were asked to like plug in the right answer, you would say maybe the Q of the reaction is equal to negative 2,890 joules. And remember that negative is just letting us know as scientists that it's an exothermic process, right? It's releasing the energy. All right, on to the next. We've got a video in the PowerPoint slides about hand warmers I would like for you to watch. It tells you about the chemistry behind hand warmers, but the flip of a hand warmer is the ice pack. So one way to make an instant ice pack is to dissolve solid ammonium nitrate in water, because that cools the solution. That's an endothermic process. So here's our question is, when 3.21 grams of solid ammonium nitrate dissolves in 50 grams of water at 24.9 degrees Celsius in a calorimeter, the temperature decreases to 20.3 degrees. Calculate the value of Q for this reaction. State the assumptions you're making. So we've been stating some assumptions every now and then here, but let's talk about what we got going on here. So we have water, right? How much? 50 grams of water. And we're gonna pour in some salt. So maybe this is my like weighing boat. Bloom, dropping in salt, and salt's dissolving. There's my salt, solid. And as the salt is turning from solid to aqueous, so it's a phase change, as it's dissolving and becoming aqueous, that is absorbing heat from the surroundings. So our system is the salt dissolving, it's the phase change, and our surroundings, it's the water, it's the cup that it's in, it's the thermometer that's monitoring the temperature. But again, the cup is negligible and so is the thermometer. So that's part of your assumptions. You're assuming that the cup and the thermometer do not absorb significant amount of heat. It could be true, it could be false. Not so much the thermometer, but the cup. Some of those cups, those calorimeters can have absorbed some amount of energy to heat up the cup. But anyway, so those are our assumptions. So we're not gonna calculate the heat absorbed from the cup or the thermometer. So this is pretty much similar to the one that we just did, except for positive Q of the reaction, because remember it's an endothermic process, is going to be equal to the negative Q of the water. Because the water is the one that's providing the heat, is releasing heat. And the reaction, the dissolving process itself, that physical change is absorbing that heat. So yeah, here we are again. So we say that the heat of the reaction, so they just want Q of the reaction. It's going to be equal to the specific heat capacity of water times by the mass of water times by the change in temperature of the water. Specific heat capacity is 4.184 joules, grams, degrees Celsius. The mass of water, they even told us immediately, the mass is 50 grams. And the change in temperature, let's see, it started, change in temperature, delta T is always final minus initial. The final temperature was 20.3 and the initial temperature was 24.9. So if you subtract those two numbers, you get negative 4.6. And remember that negative sign is the same negative sign that I've got right here, right? So the change in temperature lets you know whether or not that reaction is endothermic or exothermic. So times by 4.6 degrees Celsius. I'm going to leave it neutral because I'm going to put that negative sign up front right here. And then I'm going to erase this to give me some space. Okay, so I think all we have to do now is crunch the numbers. So the Q of the reaction, what is 4.184 times 50 grams times 4.6 degrees, and I get 962 joules. That would be negative. So positive Q reaction is equal to the Q of the system for water, which was negative. So if you were asking what's the Q of the reaction, you would say that it's positive 962 joules. Now remember, that positive sign's letting us know that you know and I know that it's an endothermic process. All right, I think we're almost to our last example here, which is here we've had our bomb calorimeter. All right, so that was that really that fancy one. It's expensive, reliable. This one is at constant volume, okay? So I'd like for you to know that. So bomb calorimeters, because the way they're assembled, which there's a video on the next slide for you to watch, they're always going to be under constant volume. So the pressure inside here can change, and the pressure is going to change because the oxygen is going to be absorbed and you're going to create gas molecules like CO2, H2O, maybe some SOX or NOx, depending upon what your sample is and what atoms are in that sample. But I would like for you to know that bomb calorimeters are under constant volume. Remember, coffee cup calorimeters are under constant pressure. So the volume actually could change if it got hot enough. So here's again that video I'd like for you to watch, but let's work the last example problem for this section, which is a bomb calorimeter problem. So here it is. So when 3.12 grams of glucose is burned in a bomb calorimeter, the temperature of the calorimeter increases from 22 to blah, blah, blah. The calorimeter contains 775 grams of water, and the bomb itself has a heat capacity, oh, here we go, of 893 joules per degree Celsius. How much heat was produced by the combustion of glucose in the sample? So if we think about our bomb calorimeter, we've got surrounded by water on the outside, and here's our bomb, and inside it's got oxygen and sugar, glucose. Okay, that's ignited from those little electrical cords, bling, and that creates a combustion reaction, and that gives off heat and heats up the water outside the bomb. Okay. So what's our system and what's our surroundings? So system, surroundings. So the system is the oxidation reaction, the combustion reaction. Combustion reaction. The surroundings, so the water, we got a thermometer right here, right? So the surroundings are going to be the water, the thermometer, and the vessel, which is the bomb itself. Okay, so the thermometer is still negligible. We don't care how much, honestly, heat the thermometer absorbs. But this time, look, the bomb itself has a heat capacity, so it absorbs energy. So for every 1 degree that the bomb increases, that absorbs 893 joules of energy. So we have to now include this in part of our surroundings. So before, when we were just saying that negative Q of reaction is equal to Q of water, now we have to add plus the heat from the calorimeter, so Q cal. All right. The Q of water was still all the same specific heat capacity stuff. What are we trying to solve for here? How much heat was produced from the combustion reaction? So we just are solving for Q, for heat. Okay, they gave us grams up here, but guess what? We don't need it. But that's why I was wondering what we were solving for. All right, so the Q of the reaction, how much heat? So we blow out our Q for water, which is just the specific heat capacity of water times by the mass of the water times by the change in temperature of the water. But now we have to add the Q cal. And the Q cal is going to be the heat capacity, which is in joules degrees Celsius, the heat capacity of the calorimeter, C cal, times by the change in temperature of the calorimeter, right? Because if you kind of watch our units down here, joules over degrees Celsius times by degrees Celsius, bing, that all cancels and you're left with joules. And energy, heat, is in units of joules. Okay, so it's just a little more complex a little more complex than what we've been looking at, but manageable, totally manageable. All right, so let's plug and chunk some numbers here. So negative Q of the reaction is equal to the specific heat capacity of water, 4.184 joules grams degrees Celsius, times by the mass of water, which is 775 grams, that's straight from the question, times by the change in temperature. What's this change in temperature? It's going to be 35.6, ready? Always final minus initial, less 23.8, and that is 11.8 degrees Celsius. Plus, now I've got to do my Q-cal from the calorimeter. So plus 893 joules degrees Celsius times by the change in temperature, which is 11.8 degrees Celsius. Let me get my eraser here. Erase this stuff down here and give myself some space. All right. So if I crunch all these numbers, I get, so negative Q, the reaction, is equal to 4.184 plus, no, sorry, multiplied by 775, multiplied by 11.8, and that value for QH2O is 38262. How about 3? Plus, and now I'm going to, so that's this piece, that's the Q, that's our QH2O, plus the Q from the calorimeter itself. So that's the heat capacity of the calorimeter, 893 joules per degree Celsius, times by the change in temperature in degrees Celsius, and that is 10,537 joules. It's joules too. That's Q-cal. So look, that almost took like a fourth of the amount of energy that was from the water. Geez Louise, right? So then to find the total Q of the reaction, how much heat was given off, it's going to be the sum of how much the water absorbed and how much the bomb calorimeter itself absorbed. And so we add those two numbers. So 38263 plus 10,537, and we get, how many sig figs do I need at the end of the day? 48,800 joules, or I guess you could call that 48.8 kilojoules. And I guess, remember, it's negative because you would be saying that it's releasing that energy. All right, so with that said, that finishes up the section on calorimetry.